When determining whether a reaction is reversible or not in an acid-base sense, it's good to use a pKa table. Here's an example of a pKa table that you really should memorize. These are different functional groups you'll come across in Chem 343 and Chem 345. So, first of all, a pKa table is a measure of acidity. The low numbers are strong acids. The high numbers are weak acids. Now, in the case of an acid-base reaction, you have an acid reacting with a base. Say, start out with HCl plus water. And this gives H3O plus and Cl minus. Now, determining on whether or not this reaction happens or not is you must take a look at both sides and identify which one is the acid. Like HCl on the left side is the acid because that's the one that gives up its proton, gives up the H. Remember, acids, in terms of Bronsted-Lowry theory, acids are proton donors. Bases are proton acceptors. So on the left-hand side, HCl is the acid. On the right-hand side, going backwards, H3O plus is the acid. Then we look on the pKa table to list their relative pKa's. HCl has a pKa approximately around -5. H3O plus has a pKa approximately around 0. Now, you draw the arrow in the direction of the highest number. In this case, 0 is higher than -5. If the two pKa values are within 6 of each other, you can think of it as reversible. So, in the case of HCl and water, you mix the two together, most of it will go to H3O plus and Cl minus, but some of it will stay as HCl and H2O. Now, with that in mind, we can try another problem, say between HCN, reaction between HCN and this. And you get, as a product, this plus Cn minus. Again, label the acids on both sides of the equation. This is the acid here. Its pKa is 10. Acid going backwards, here, pKa around 25. So this goes all the way to the right. The difference between the two, 25 minus 10, is 15. This reaction is hardly reversible. Now, think about pKa. We're talking about a logarithmic scale. HCN is 10 to the 15th times stronger acid than a terminal acetylide. Hence, this will readily protonate this to give you a terminal acetylide, but cyanide will hardly deprotonate a terminal alkyne to go backwards. Say we have a case of dimethylamine plus phenol. And so dimethylamine has a hydrogen on it. Add these together. Get this. When you're comparing these two, the one that gets the proton to go this direction is the dimethylamine. That means this is the proton donor. This is the acid. To go backwards, this donates its proton to phenol. So this is the acid here. Both of them have pKa's around 10. That means you're in complete equilibrium and equal probability of going back and forth. Now, we could do is if this was actually the acid, then the problem changes somewhat. So if that nitrogen actually gives up its proton, get something like this. Well, in this case, this is acting as the acid because that gave up its proton. So instead of using 10, we're going to use a pKa of 35. This, on the other hand, has a pKa of 0. It's the closest one to the chart. Here, the answer is a resounding, it goes to the left. So, what this is saying is, if you mix this plus this, dimethylamine plus phenol, you do not get a deprotonated nitrogen and a protonated oxygen. What you do, on the other hand, get is a deprotonated phenol, so you get phenoxide plus the ammonium. So you can use sort of acid and bases to predict what two molecules will go together just by using this simple pKa table.